Well, thank you very much. Good morning to everyone. I'm Nicolás Pacerini, and together with Carlos Lombardi, we want to share with you some ideas about how we teach object-oriented programming to first-year university students. So, when we started teaching object-oriented programming like 15 years ago, we took a course with huge dropout rates. So we started looking for strategies that would allow us to improve the course results. And we found out that this, in fact, is a very common phenomenon. Learning how to program is not easy, and OOP has been frequently reported to show even more difficulties than other programming paradigms. Among all the possible reasons for these failures, we found one that is particularly relevant for teaching OOP, which is the high amount of abstract concepts that the student is required to understand to be able to start producing his own programs. Frequently, the most simple examples require the usage of concepts such as class, subclass, inheritance, different types of scopes, data types, different types of variables, packages, and so on. In this scenario, we have seen proposals of postponing the introduction of OOP, but we don't like that. We think that OOP is quite relevant to professional practice, so we wanted to allow it to have a big amount of space in an engineering curricula. So postponing it to an advanced course would not allow for the required space. So the main objective of our proposal is to reduce the amount of concepts that are necessary to create a first working program, avoiding to overwhelm students, being able to put those concepts into practice as soon as possible, and without falling into didactic transpositions that oversimplify those concepts in a way that the contents of the later part of the course would conflict with these initial definitions. For that matter, we created an incremental path involving a sequence of meta models where each of them introduces a few more concepts without conflicting with the previous ones. We start with the simplest possible meta model that could create a complete working object and allows us to focus first in the concept we consider most important for OOP. Those concepts are object, message, and polymorphism. And the most significant change to a normal course is that we postpone the introduction of classes, sometimes to the second half of the course. The question that you may be asking is, what can we do without classes? So for that to be possible, we created a large set of examples tailored for each intermediate meta model, and also a large set of tools, including a specific language, which is named Wolog, and some programming tools customized for this purpose. So in the following, we are going to describe the first meta model and show what all can be done without introducing classes. This is the first example, one we use sometimes in class. It's an object defined in terms of this initial meta model we proposed using a minimal set of concepts. We have a working definition of an object respecting OOP principles. The syntax matches precisely the concept we want to teach and in the way we explain them in class. We have objects, variable, method, return values, parameters, and no much more. So also in the REPL, we allow the students to play and test his production immediately, sending message to the created object. And I think now, yeah.
As Nicolas exposed, we begin with the minimal meta model. In this slide, we show that this minimal meta model suffices to work with several of the main concepts of OOP, as polymorphism and interaction among objects, as early as in the first or second lecture on an initial course. To this end, we introduce a variation of the Pepita object in which the eat method takes two parameters, the first one being the food that Pepita actually eats. In this variation, the amount of energy that Pepita gains for each gram depends on the kind of food. We propose to the students the addition of objects that model the different kind of food that Pepita could eat, and ask them which feature this object should expose. Most of them quickly grasped that the object that models food should be able to answer to the energy per gram query, since this is the query Pepita asked them for. Hence, all objects that model kinds of food must include a method with that name. We work with several sub-objects. Some of them, like the canary grass, have a straightforward implementation of the energy per gram method, while in other cases, like the millet, its determination involves some computation. We can show here that Pepita ignores how simple or complex it is to compute the energy per gram for a given food. Pepita just knows it can ask for this information. Hence, this simple example allows to introduce several key aspects, mainly polymorphism that is intuitively perceived by most students, but also collaboration among objects, communication through well-established interfaces, and information hiding. Wallock includes many features that improve the course experience for both students and teaching staff. We highlight the dynamic diagram, which is shown upper left, that shows the object mentioned in a REPL console and the relationships among them. This diagram is very useful in the teaching of several concepts, as how a net of interacting objects is created and how the behavior of an object can depend on its collaboration. Later on, when we introduce classes, it shows clearly that each instance is an independent object having separate attributes. Wallock also includes features that enable the production of automated tests, upper right. The language includes a syntax for test definition similar to that found in several industrial tools. The environment, in turn, includes a facility to run these tests and show the results. Students start writing tests well before the introduction of classes and instantiation. We also remark that the Wallock language includes collection literals and a functional interface for collections. These features allow to work with collection and functional-like traversals also before classes are introduced. We remark that Wallock is an open source product, so we hardly invite you to play with it in www.wallock.org. So next one. When the time comes to introduce classes, several features contribute to ease the transition. Syntactically, we see that a class definition is almost identical to that of a self-defined object. We just write class instead of object in the first line and capitalize the name. The attribute and method definition are identical. Hence, once the students begin defining classes, they already know how to write them. Furthermore, this happens on the 6th or 7th course week, so that the student already have passed through extensive activity defining objects, using them, and made them interact. Therefore, the new concepts integrate into an OOP mental model that is already quite developed. As a result, we don't note in our courses the confusion between the concepts of instance and class that is repeatedly described in the literature. So next. The class experience using these ideas and tools spans about 20 courses, 5 universities, and a rough total of 1,000 students each year. These are some of the main conclusions we obtain. Firstly, that our proposal allows students to experiment with objects from the very first week, to define their own objects from the second one, and to write tests no more than 1 or 2 weeks later. Secondly, that the conceptual framework of OOP is presented gradually, making much more easier for the students to understand its elements, and most important, to use these elements properly in program building. Thirdly, that the existence of adequate educational tools has a paramount importance. In fact, having a tool as a Wallock language and environment basically enables the way we propose to introduce OOP. And lastly, we want to stress the fact that while far from the focus of the paper we're presenting, is very important to us. Namely, that keeping in close contact with the students, giving frequent feedback, contacting actively the students showing difficulties, and promoting a sense of community in each course has a great impact on student attitude and ultimately on pass rates. Finally, uh, among the future directions we envisage for this line of work, we highlight the last item described in this slide, namely word game that Nicolas knows about it much more than me, so he can explain a little bit.
So Wallet Game is a feature we've been working on and looks very promising. In some courses, we introduce Wallet Game only after 3 or 4 weeks. It provides a very simple framework to create games, rather simple, designed for being easy for beginners to be able to create simple games on top of it, but students are very creative and have created really cool games. The first games, they have only a handful of simple objects, unique objects that do not require the introduction of classes, and they are very motivating for students as they allow not only to play but also to create real programs that have a meaningful behavior. And they also provide really cool concrete examples for the needs of some abstract and complex concepts such as first class functions. So we are very excited about working on this idea. And that would be it, I think. Thank
So
you.
thank you very much for your attention.